So as we've been doing for the past couple of days, we're going to keep trying to learn how to determine when series converge and diverge. And we're going to spend a lot of time on this. And so it's going to be a slow but steady process of just dealing with different types of series and seeing if any of our previous methods work. And if not, then coming up with a new test. So let's look at this one. So we really have three tests that we've learned so far. We can see if it's geometric, if it's harmonic, or if the test for divergence works. So let's just kind of work through each of those here. So maybe I'll start with the test for divergence because that's always a good place to start. It's usually pretty easy, so we can look at the limit as n approaches infinity, 1 over n squared plus 3n plus 2. All the n's are in the denominator, so we're going to get 1 over a really big number, which is going to go to 0. Remember, the test for divergence tells us nothing, absolutely nothing when we get 0 out. So test for divergence is not helpful here. So now we can try and see whether this looks harmonic or geometric. I would tell you that by looking at the format of this, this is not going to be either of those. Geometric things usually look like a number to a power, or maybe, like we might even have pi to the n plus 1 or something like this, but we have exponents in the, or the exponents have our n's in them. We don't have n's to an exponent. So usually that's what geometric things are going to look like. So this is probably not going to be geometric, but let's just check. We can do that by writing the first few terms out. So when I plug in 0 for n, I'm going to get 1/2. When I plug 1 in for n, you can double check my work, I get 1/6. When I plug 2 in for n, I got 1/12, and then I got 1/20. So this keeps going. Okay, so to see if this is geometric, we just want to look at what do I multiply to get from one term to the next, and do I multiply this by the same thing to get between every pair of terms. So to get from 1/2 to 1/6, I multiply by 1/3. To get from 1/6 to 1/12, I multiply by 1/2. So immediately we can see that this is not geometric because the 1/2 and the 1/3 are not the same number. We have to multiply by the exact same number every time to have a geometric series. Okay, so not geometric. Test for divergence doesn't tell us anything. Remember the harmonic series looks like 1 over n. So we have things like 1 plus 1/2 plus 1/3 plus 1/4 and so forth and so on, or potentially multiples of those. And we see that this does not look like that. We already have the 1/2 in there. And this does not look like multiples of the harmonic series. Okay, so we've identified that none of the methods that we have learned so far are going to work on this one, which is always a good place to start. You probably figured that out because this is called telescoping series, and we haven't talked about that yet. Okay, so what are we going to do here? We're going to do something a little bit weird with this one, and then I'll talk about how do you know when to try this method. So what we're going to do is we're actually going to write the partial fraction decomposition for the terms of this series. So we have to think way back to last semester to do partial fractions. So remember, that's when we rewrote a rational function as a sum of two fractions. So we need to start out by factoring that denominator. That factors as n plus 1 times n plus 2. And then we write this as a over n plus 1 plus b over n plus 2. This is that partial fraction decomposition from last semester. Okay, and then, so thinking back to last semester, and if you need to review the videos from last semester, might not be a bad idea. We get rid of the denominator, so we multiply everything by the common denominator, which is n plus 1 times n plus 2. When I multiply this piece by the common denominator, everything, the denominator goes away and we're left with 1. When I multiply this by that, the n plus 1's cancel out, so I'm left with a times n plus 2. And when I multiply this term by it, the n plus 2's cancel out, so I'm left with plus b times n plus 1. Okay, and now we remember that we're trying to find a and b, so if we let n be equal to -1, then we get 1 is -1 plus 2 is 1 is a, the b term goes away. So we found that a is 1, and if n is -2, then 1 is equal to b times -1, so b is -1. Remember that I picked these numbers trying to figure out what is going to make one of these terms equal to 0. So picking -1 makes this term 0, picking -2 makes this term 0. Okay, so this is going to give us our partial fraction decomposition. We're going to have 1 over n plus 1 minus 1 over n plus 2. And so I can just say that that original series is equal to this because all I've done is rewrite the terms. Okay, so this might not seem useful yet, but what we're going to do now is we're going to start writing out the terms of the series, and the terms are really going to be the same. They're just going to be written differently because now we've decomposed the structure of the individual terms. So if I plug in 0, and I'm going to keep these in parentheses. If I plug in 0, I get 1 over 1 minus 1/2. If I plug in 1, I get 1/2 minus 1/3. If I plug in 2, I get 1/3 minus 1/4. And this is going to keep going on forever. If I just stop at the nth term, I'm going to get 1 over n plus 1 minus 1 over n plus 2. So this is actually giving us the nth partial sum, what I have here. Okay, so now look at this. Something interesting happens here. Look at that the 1/2s cancel out because I have 1 negative and 1 positive. The 1/3s cancel out. If I kept going, the 1/4s seem like they would cancel out. And it seems like this n minus 1 will cancel out with something previous. So this is what it means to be telescoping. Telescoping, if you think about a telescope, I don't know if you've ever seen a telescope. A telescope has those sections to it that can kind of collapse it or expand it. So this is like collapsing a telescope, where these pairs of terms are canceling each other out, and this telescope is collapsing to the only things that are left, which is the very first term in this case and the very last term. In telescoping series, there will always be terms that cancel out. Sometimes you're left with more than just one term at the end, though. So don't think that everything has to cancel out. So our partial sum can be simplified to 1 minus 1 over n plus 2. And so remember, the sum of the series is just the limit of the partial sums. This is not a test for divergence. This is just a limit of partial sums. Since this last piece goes to 0, this whole thing will be 1. And so what this is telling us is that the limit of our series, or it's telling us that the limit of our partial sums is 1, which means that the sum of our series is also 1. So that original series converges to 1. Okay, so this is how partial fractions, or not how partial fractions work, how telescoping series work, is that you start out by writing that partial fraction decomposition. Usually there's going to be a minus in here, so that things will cancel out. And then you start out by writing the first few terms of your series and see what cancels out. Then you look to see, does whatever's left at the end, does it go to 0? If so, whatever's left at the beginning, just those concrete terms, is going to be what your series goes to. Otherwise, if this last piece goes to infinity, then your series will be divergent. Okay, one thing we notice here is really important is that this tells us what the series converges to. We can actually get a number out. We figured out what particular geometric series converge to. Now we also know what telescoping series converge to. These are going to be the only 2 tests for convergence or divergence that tell us what a series converges to. So all of our other tests, like the test for divergence, is not going to tell us what a series converges to. They'll just tell us whether they converge or diverge. So if I ever ask you to find the sum of a series, it actually has to be telescoping or geometric, because we're not going to be able to find the sum of any other series. Just kind of a fun fact. Okay, so the time in which a telescoping series is a good thing to try is if your original expression starts out as a rational function, so a polynomial over a polynomial, and it looks like you're going to be able to do partial fraction decomposition on it. And so we'll see some examples in class, just so that you can get that practice identifying when I try telescoping series.